We left off in our previous episode with the needs for dietary requirements for the blood, and the turnover of the blood is coming up. This is part 4 of the blood, page 637, and this is actually where we left off in our previous episode. We are in a situation where we have to take on iron in order to create the porphyrin ring. And so we store the iron as either ferritin or hemosiderin, and that's in the liver, generally speaking, ferritin and hemosiderin. And then when we get to the intestine, we have a special also carrier called transferrin. So this is iron wrapped in protein in all of these different cases. And so in order to travel in the bloodstream itself, we have this special molecule that's formed for the iron. Okay, so then the fate of an erythrocyte, and it's predicated in part on A, C, and E. Remember, those are the antioxidant vitamins. I like to remember them as ACE, A, C, and E. And these maintain membranes. So as we go over this here, it says that the blood cells have a useful lifespan of somewhere in the vicinity of 100 to 120 days. That's about the time it takes for complete repair of a fracture, as it turns out, is 100 days. So I think there's a relationship there, but you'll need to think about it a little bit. At any rate, it says that a nucleate condition carries with it some limitations. For instance, they cannot, as they say here, make or synthesize new proteins, and so they can't necessarily repair themselves. So they are as good as they are as sort of like initially created in the bone marrow. And so A, C, and E plays a role in maintaining the membrane so it does not become fragile, is the idea here. Eventually, red blood cells do lyse, and they're usually taken up in the spleen in most cases, and then transferred from the spleen over to the liver. There's a little diagram here that discusses that. So the blood cells, the red blood cells, are made in the bone marrow, released, and then recovered. Here they are. This, you'd have to think of this area as maybe the spleen, the sinusoids of the spleen, and we're going to be taking up the constituent parts. It says here that the iron, the core iron, is salvaged and bound to protein, such as ferritin or hemosiderin. So that's recycled, and the heme groups that are formed as a pigment originally then become bilirubin, ultimately biliverdin, a green-colored substance, and they get turned over as bile salts ultimately. So the iron is salvaged. Some of the red blood cell is salvaged as in order to make the bile for the liver, which emulsifies fat in the small intestine. And there's always membrane recovery for making new membrane. All of the constituents are pretty much recycled in that regard. We talk about erythrocyte disorders mainly as anemias, if they are being, how shall I say, destroyed in some ways or prevented from developing. So initially there could be a simple loss in the sense of hemorrhagic anemia, so blood loss. This is something that might happen during surgery or during traumatic events, occasionally during such events as childbirth or amenorrhea. There's quite a few things that could cause this problem. And then there's not enough red blood cells being produced. This could be, they give us some subtitles here in terms of subcategories. Iron deficiency, that is to say, we have a diet that lacks iron, And usually we need iron in the presence of vitamin C in order for it to work, to be taken up. And then we come over here to pernicious anemia. Pernicious anemia is occasionally thrown out by certain, how shall I say, constituents of the public when they're concerned with veganism versus meat eating and so on. But it turns out not to be so much an issue of vitamin B12 as it is an issue of intrinsic factor. So in the absence of intrinsic factor, it's difficult to move vitamin B12 around. Vitamin B12 is actually stored with its intrinsic factor for long periods of time because very little of it is needed. It has recommended daily requirement of something in the vicinity of 2 micrograms, which is a very small, indeed small amount. And we'll come over here for just a second to take a look at the strange shape of B12. This is B12, and it is indeed a strange molecule, not something that is able to easily slip across a membrane. And so we have to create sort of a wagon-like device out of protein, and that would be the intrinsic factor. So this very sort of unwieldy molecule will fit into the wagon in which it's carried, and it's then able to go across membranes because of the nature of the intrinsic factors. Transmembrane protein can get it through. So we have special facilities, shall we say, for this particular vitamin. Okay, so mostly this vitamin would be lacking only under certain conditions, one of which is no intrinsic factor. Some people are born without intrinsic factor, so they have to get shots, and they have to get special treatment from the medical profession. Other people, you worry about possibly veganism because of the source materials for this actually would be from the animal kingdom, but mostly you can get it from your flora, dietary flora. And so you would have to encounter at some point or another a vegan individual who was taking wide-spectrum antibiotics for many years. And maybe under those conditions there could be it's hard to imagine, though. It's just very, very hard because we store this particular vitamin for as much as 8 or 10 years. So that would be a very rare condition in which there wasn't enough B12. It really has to do with intrinsic factor. So then we press on here to the renal anemia. It says here caused by lack of EPO. So it's possible that in kidney decline that the kidney is insufficiently creating sufficient amounts of erythropoietin, and so we are not able to stimulate the synthesis and reproduction of stem cells into mature blood cells of various kinds, including erythrocytes. Okay, then aplastic anemia is there's an interference with the synthesis. There could be destruction or inhibition, it says here, of the red bone marrow. And these types of things happen because of drug therapies, various kinds of chemical poisonings that might occur. And then there's also ionizing radiation. Certain viruses also can interfere with that. Too many red blood cells is an abnormality that usually is associated with blood doping more than anything else. And occasionally it could be in the white cells, an aspect of leukemia. Okay, the other problem that might occur here is that the hemoglobin itself is malformed, and so thalassemias exist, as well as sickle cell anemia. In thalassemias, we have one of the globin molecules of the 4 that has been altered in some way or missing, and then the sickle cell anemia is this situation right here, and as indicated that once this formation occurs, it's very disruptive to oxygen uptake.